today's lesson, we will tackle about the digraph. So first, what is digraph? A directed graph, also called a digraph, is a graph in which the edges have a direction. In mathematics, and more specifically in graph theory, a directed graph or digraph is a graph that is made up of a set of vertices connected by directed edges, often called the arc. Here are the example of a simple directed graph. In formal terms, a directed graph is an ordered pair, or more simple, is a collection of vertices and edges. So we can say that the graph G is an ordered pair of the vertices and edges, where V is a set whose elements are called vertices, nodes, or points. And A is a set of ordered pairs of vertices called arcs, directed edges, or sometimes simple edges with the corresponding set name E instead of A, arrows, or directed lines. It differs from an ordinary or undirected graph in that the latter is defined in terms of unordered pairs of vertices, which are usually called edges, links, or lines. V or vertices represent the dots. We can label it if we want, like dot A, B, C, and etc. And A or E, or the edges or arcs, or the lines that connected the dots, or the vertices are between the dots. Here are the example of what edges looks like. We can label it also edge D, E, F, and etc. These two lines or edges are different. As you can see, the first one is just like a line segment and the second one is a ray. This line used in undirected graph and this line used in directed graph. Undirected graph, there is no direction or order does not matter. In directed graph, order does matter. This is the example of undirected graph. So how we can collect the vertices and edges of undirected graph? We list every edge as a set of vertices, and edge D is going to be the set of A and C, so it connects A to C. Same thing with the set C and A, they are exactly the same because there is no direction or ordered does not matter. But in directed graph or direct graph, order does matters. So we can label this ordered pair. The edge D goes to C to A. So here, we can determine the ordered pair which we have the tail coming from C and we have a head going to A. The edge D, it goes from C to A is not equal to goes from A to C. But if we put an edge like this, we can label it edge G, and a set of vertices goes from A to C. These two sets are really different. Edge D goes from C to A and edge G goes from A to C. These two sets are not equal. Just take note, if the edge has an arrow, it is the digraph or directed graph, and if it doesn't have an arrow, it is used in undirected graph.
Equivalence relation. Equivalence relation is a binary relation that is reflexive, symmetric, and transitive. Equivalence relations are often used to group together objects that are similar or equivalent to in some sense. Each equivalence relation provides a partition of the underlying set into disjoint equivalence classes. Two elements of the given set are equivalent to each other if and only if they belong to the same equivalence class. A relation R defined on a set A is called an equivalence relation if R satisfies the following. Reflexive, where AA is an element of R, for all A is an element of A. Symmetric, where AB is an element of R, then BA is an element of R, for all A, B is an element of A. Transitive, where AB is an element of R and BC is an element of R, then AC is an element of R, for all A, B, C is an element of A. Rule number 1. A is equals to 0, 1, 2. R1 or relation 1 has ordered pairs of 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, and 2, 2. R1 is reflexive because it has ordered pairs of 0, 0, 1, 1, 2, 2. It is also transitive because it has 0, 1, 1, 2, 2, 0, and it is also symmetric because it has set of ordered pairs 0, 1, 1, 0, 2, 0, 0, 2, 1, 2, and 2, 1. Example number 2. A is equals to 0, 1, 2, 3. Relation 1 or R1 has set of ordered pairs of 0, 0, 0, 1, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, and 3, 3. R1 is reflexive because it has 0, 0, 1, 1, 2, 2, and 3, 3. It is also transmittive. Example number 2. A is equals to 0, 1, 2, 3. R1 or relation 1 has ordered pairs of 0, 0, 0, 1, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2, and 3, 3. R1 is reflexive because it has ordered pairs of 0, 0, 1, 1, 2, 2, and 3, 3. It is also transitive because it has 0, 1, 1, 2, and 2, 0. It is also symmetric because it has 1, 2, and 2, 1 of ordered pairs. So R1 is an equivalence relation. Next, R2 or relation 2. R2 has ordered pairs of 0, 0, 0, 2, 2, 0, 2, 2, 2, 3, and 3, 2, and 3, 3. R2 is not an equivalence relation because first, it is not a reflexive because it doesn't have a ordered pairs of 1, 1 or an ordered pair with the member 1. So it is not reflexive, then it is not a equivalence relation. Always remember that if reflexive, transitive, and symmetric are all satisfied in a relations, then it is an equivalence relation.
Equivalent classes. In mathematics, when the elements of some set S have a notion of equivalence, then one may naturally split the set S in the equivalence classes. These equivalent classes are constructed so that elements A and B belong to the same equivalent classes if and only if they are equivalent. Equivalent classes is the name given to a subset of some equivalence relation R which is include all the elements that are equivalent to each other. Let A be a set and let approximate be an equivalent relation on A. For an A is the element of set A, we define the equivalent class of A by open bracket A close bracket is equal to open bracket X is the element of A colon A is equivalent of X close bracket. The element of A is called a representatives of the class open bracket A close bracket. The value of X is equal to open bracket Y is the value of X and Y and the element of relation. Equivalent class of X is the element of set A. Example number 1. Let set A is equal to Y is the value of 1, 2, 3, and 4. Define a relation R on set A by relation is equal to 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, 4, 4. Relation is an equivalence relation. We know Determine its equivalence classes. First, consists of all elements. X is the element of set A such that 1 relation X. Examining R, we find that 1 relation 1, 1 relation 2, 1 relation 3, and 16 relation 4. Hence, 1 is equal to 1, 2, and 3. Now, consists of all elements. X is the element of set A such that 2 relation X. Examining R, we find that 2 relation 1, 2 relation 2, 2 relation 3, and 26 relation 4. Hence, 2 is equal to 1, 2, and 3. Similarly, 3 is equal to 1, 2, and 3. Finally, 4 is equal to 4. Since the only X is the element of set A with 4 relation X is X is equal to 4. We note that there are two equivalence classes in a set A, namely 1 is equal to 2, is equal to 3, is equal to 1, 2, and 3, and 4 is equal to 4. Example number 2. Let set A is equal to 1, 2, 3, 4, 5, and 6, and define a relation approximate on set A by relation is equal to 1, 1, 1, 3, 2, 2, 2, 4, 3, 1, 3, 3, 4, 2, 4, 4, 5, 5, 5, 6, 6, 5, 6, 6. Then, R is an equivalence relation. We will determine the equivalent classes of R. To determine, we look for all of the ordered pairs. 1x is the element of relation. We see that the only x which work are 1 and 3. Hence, 1 is equal to 1 and 3. Similarly, 2 is equal to 2 and 4. 3 is equal to 1 and 3. 4 is equal to 2 and 4. 5 is equal to 5 and 6. And 6 is equal to 5 and 6. We note that there are 3 equivalent classes since 1 is equal to 3, 2 is equal to 4, and 5 is equal to 6.
Congruence. Congruence are an important and useful tool for the study of divisibility. As we shall see, they are also critical in the art of cryptography. As with so many concepts, we will see congruence is simple, perhaps familiar to you, yet enormously useful and powerful in the study of number theory. Two integers a and b are congruent modulo m if and only if they have the same remainder when divided by m. So when we say congruence, if the two integers are the same have the same remainder when it is divided by m, which is m, we called as modulus. So if a and b are integers and n is greater than 0, we write a is a congruent of b mod n, to mean n is divided by b minus a, so read as a is congruent to b modulo n or mod n. For example, 29 is a congruent of 8 mod 7, to mean 7 divided by 29 minus 8. So to prove that this is a congruent, 29 we will divide to 7, which is equals to 4, and it has the remainder of 1, while 8 we will divide by 7 is equal to 1, and it has also a remainder 1. So the two integers are congruent because they are the same remainder. Example number 2. 8 is congruent of 3 mod 5. To mean 5 is divided by 8 minus 3. So we will divide 8 divided by 5 equal to 1, and it has the remainder of 3. And while 3 divided by 5 equal to 1, and it has also a remainder of 3. So this is a congruent because they have the same remainder. Something important to know that in proposition, congruent modulo n is an equivalence relation. That is, for any integers a and b and positive integer n, we have A is congruent of A modulo N. So this results as classified to reflexive. And 2, if A is congruent of B modulo N, then B is congruent of A modulo N. So this is classified as symmetry. And last, if A is congruent of B modulo N and B is congruent of C modulo N, then A is congruent of C modulo N. So these results classified as we called transitivity.
Partial order. A partial orders define a notion of comparison. Two elements, X and Y, may stand in any of four mutually exclusive relationship to each other. Either X is greater than Y, X is less than Y, or X is equals to Y, or X and Y are incomparable. A set with a partial order is called a partially ordered set, also called as a poset. Partial order define a binary relation R on a set S is called a partial ordering or partial order if and only if it is reflexive, antisymmetric, transitive. Poset, a set S together with partial ordering R is called a partial order set or poset denoted. It is essential to mention that the symbol used for partial ordering looks like the inequality less than. It is merely symbol representing n relations. Thus, we could denote a poset at S, R, where R is some relation. Example is in this photo. Partial ordered symbol partially ordered relations. Now, the three fundamental partial order relations are less than or equal to. Subset, divisibility. For example, let's show that divisibility is a partial order relation on A. A set of R is equals to A, B, element AX, A, and A, B, or A of element of Z. Reflexive is for all A, element A, or A, A, element R. AA and A to element A. Antisymmetric. If A, B, element R, and B, A is element R, then A is equals to B. AV then BA only if is A equals to B. Transitive. If A, B, and B, C, element R, then A, C is equals to R. AB and BC then AC, partial ordered divisibility. And then you know that the reason why a partial ordering has the name that it does is because pairs for element or task can be either comparable or incomparable. Consequently, some pairs of elements or tasks must come before another comparable, or they do not need to come before but can be performed simultaneously or separately incomparable. For example, these are the following tasks that Sparky, a discrete mathematics student, does every morning upon waking up, shower, breakfast, put up on pants, shirts, socks, shoes, watch, and jackets. It is highlighted in the haze diagram below. What is so important to note is that Sparky can put on pants, socks, or shirt in order, as it doesn't matter if Sparky puts on a shirt before putting off pants. But other tasks must be done in order, as it wouldn't make sense to put shoes on before socks. This is the idea behind partial ordering, where tasks that there are ordered are considered compatible and that those tasks that are unordered are called incompatible. This is an example of topological sorting and helps project managers with scheduling application in a real-life application for partial ordering. Partial order versus total order. Comparability means that the elements A and B of a poset S greater than B greater than S are comparable if either A, V, or B, A. In other words, task A must come before B or task B must come before A. If S greater than is a poset and every two elements of S are comparable, then S is called a totally ordered set, sometimes called a linearly ordered set or chain. For example, the set of integers over the relations less than or equal to is a totally ordered set because for every element A and B in the set of integers, either A greater than B or B is greater than A, thus showing ordered Hayes diagram. The best way to graphically understand and represent partial orders is via a Hayes diagram. Excuse me. A Hayes diagram is a graph for a partial ordering that does not have loops and arcs, that imply transitivity and is drawn upward, thus eliminating the need for directional arrows. Hayes diagram is a graphical representation of the relation of elements of a partial ordered set or poset with an implied upward orientation. A point is drawn for each element of the partially ordered set, in join with the line segment according of the following rules. If P less than Q in the poset, then the point corresponding to P appears lower. Excuse me. In the drawing, then the point corresponding to Q. The points P and Q will be joined by the line segment if P is related to Q. To draw a Hayes diagram, provided set must be a poset. A poset or partial ordered set A is a pair of B of a set V, whose elements are called the verticals of A and obeys following rules. Reflexivity. Phi, B. Antisymmetric. P, Q, and Q, P, if P is equals to Q. Transitivity, if P, Q, and Q R, then Phi R. Example, 1 draw Hayes diagram for 3, 4, 12, 24, 48, 72. Explanation. According to above given question, first we have to find the poset or the divisibility. Let the set is A. A is equals a set of pairs 3, 12, 3, 24, 3, 48, 3, 72, 4, 12, 4, 24, 4, 48, 4, 72, 12, 2, 4, 12, 4, 8, 12, 72, 24, 48, 24, 72. So now, this diagram will be 72 to 24 to 48, 24 to 12, 12 to 4, and 12 to 3. In above diagram, 3 and 4 are at the same level because they are not related to each other. And they are smaller than other elements in the set. The next succeeding elements for 3 and 4 is 12. 12 is divisible by both 3 and 4. Then 24 is divisible by 3 and 4 and 12. Hence, it is placed above 12. 24 divides both 48 and 72. But 48 does not divide 72. Hence, 48 and 72 are not joined. We can see transitivity in our diagram as the level is increasing. Example 2. Draw Hayes diagram for D. Explanation here. D means set of positive integers divisors of 12. So, D is equals to set of 1, 2, 3, 4, 6, 12. So, partially ordered or O set A is equals to 1, 2, 1, 3, 1, 4, 1, 6, 1, 12. So, 2, 4, 2, 6, 2, 12. 3, 6, 3, 12, 4, 12, and 6, 12. So now, this diagram will be 12 to 4 and 12 to 6, 4 to 2 and 6 to 2, 6 to 3 and 2 to 1 and 3 to 1. In above diagram, 1 is the only element that divides all other elements and smallest, hence it is placed at the bottom. Then the elements in our set are 2 and 3, which do not divide each other, hence they are placed at same level separately but divisible by 1, but joined by 1. 4 is divisible by 1 and 2, while 6 is divisible by 1 and 2 and 3. Hence, 4 is joined by 2 and 6 is joined by 2 and 3. 12 is divisible by all the elements, hence joins by 4 and 6, not by all elements because we have already joined 4 and 6 with smaller elements accordingly.